I have the great pleasure of hosting Dr. Travis Oliphant. So, Dr. Oliphant, thank you so much for your time and for doing this podcast.
Oh, it's a pleasure. And you can call me Travis. Thank
Travis,
you.
okay. Okay, wonderful. So, I would like to start our discussion with NumPy. So, what originally inspired you to develop NumPy and what gaps were you trying to fill?
Yeah, so NumPy is a big project. And now, of course, it's led by hundreds of people that do a great job of maintaining it. And NumPy 2.0 just came out, led by some of the people at Quansight Labs. But the original NumPy was started because I was concerned about the community splitting. So there was a project called Numeric, which is written by Jim Huguenin back in 1995 as he was a grad student at MIT. And I was using Numeric. And then I started the SciPy project using Numeric as a foundation. And in 2004 or 2001, 2002, another array library called NumArray was being written by my friends at the Hubble Space Science Telescope Institute, STSCI, and Perry Greenfield, Todd, a few other contributors there. They were involved in making NumArray, and NumArray added features that were important. There were shadow arrays, there were faster at big array computations, more data types. There was several things they were adding. Advanced indexing operations, the index with integers and index with mask arrays, for example. These are important features that people were asking for, and NumArray was adding them in a separate array library. So fast forward a few years, and now there's two array libraries, and more importantly, there were a lot of downstream libraries that were being written requiring one or the other array library. And I saw that, and it was just frustrating as somebody who was excited about the unification, about the growth of scientific Python, about the fact you could use Python to do a lot of science, that this is going to fracture the community and make it harder for people because, oh, I'm on this integration library and it needs numeric, and oh, I want to install this image processing library, but it needs NumArray. So now you're going to have two array libraries. You're not going to remember which one it is, and the interchanges weren't very good. I just didn't like that. I thought this is not good for the community to grow, and it was a small, young community. And so I had some time, and I said, "Well, who's going to do something about this?" Nobody's going to do something about this. And I was already a contributor to Numeric. I had written a lot of extension modules with SciPy, so I knew the C code base. I knew things. I'd written C and Python, and the NumPy extension is in C. So I knew a lot about it. And so I said, well, I've got some time. And so I just started, and I told the community I was going to start this. And, took about 4 months to build the first version and about 14 months to debug it and fix it and make sure it could actually be used with with a host of other contributors who helped. And that's where it came from. It came from my desire to help unify the array communities to make sure we didn't split and we got more cohesion. So that's where it came from. That's why we wrote NumPy.
About the next project, which is SciPy. So, how has your background in electrical and biomedical engineering shaped your approach to building SciPy?
That's a good question. So SciPy, as you may have inferred, a lot of people know me for NumPy, but SciPy was first. SciPy was the very first thing I started to do, and it emerged from a collection of extension modules to Python that I was writing. My background was electrical engineering. Then I went to the Mayo Clinic and studied biomedical engineering, and was doing ultrasound and MRI image processing and signal processing. And so I had a lot of background in probabilistic reasoning and image process, signal processing. But I was using MATLAB, or I was using IDL was starting to get used as well. And I wanted to use Python. And then I was writing C programs and C++ programs. So that influenced me because I liked Python because it was just the steering language, because I could just write high level scripts that would then call out to functions that were in native code. And I knew how to write those native codes. And so, but I wanted certain things to be available. So, for example, I was writing a MRI simulator. So MRI, magnetic resonance imaging, it's very interesting physics, very interesting problem you're solving. But at the core is an ordinary differential equation system of equations called block equations. And I wanted to simulate those. And that's basically solving an ordinary differential equation and a bunch of them. But I wanted to do that from Python, so I had to find an ordinary differential equation solver. Now, I didn't write one. I just went to the internet at the time. There was a library called Netlib, or a web page, and it had 4chan implementations of the LSOTA, particular approach to solving an ordinary differential equation. And I just wrapped it. I wrapped it and made it available so a Python user could take a numeric array, organize their problem, and then solve it. There was a few technical details that were important to solving that. So it was the problems I was trying to solve. I was trying to scratch my own itch that led me to build, and then the ability Python gave you to extend it. And then, so I did it. And then it was what I found, that it was really fun to put the module out on the internet. And by today's standards, it was terrible in terms of usability, because it was literally just, here is a tarball, a tar.gz of source code, and then a little readme about what it does, and maybe a little example about how to use it. And I'm surprised it got any users at all.
Was it difficult for you to write all that documentation for NumPy and SciPy?
Oh, for sure. But it was really important, and I didn't write all of it myself. I think one of the key things about open source projects is the successful ones get a group of people around you to help. Like, in no way could NumPy and SciPy have been successful on my own. Like, it just wouldn't have happened. Like, so some of the most important things that I did early with SciPy is just collaborate on the mailing list. First of all, I'd communicate, here's something I did, and then I'd follow up with people that made changes and patches. And then, SciPy came about because I was doing some work, and then a guy named Eric Jones, who was at Duke, was doing his research and was starting to use Python in some of the modules I was writing, and he had his own modules. And he called me and said, well, why don't we put these together into a library and call it SciPy? So, he was the origin of the name SciPy, but he took these libraries. I'd been working on some of his. Then another colleague, Piaro Peterson, who's in Estonia, who was one of the first people that it kind of got me excited about collaboration, because I'd never heard of Estonia at the time. I didn't even know where it was. But here he was downloading my package and then sending me back change, saying, hey, why don't you change the make file like this? Or, here's a feature you could add here. And I'm like, oh, this is great. This is fantastic. This is the kind of collaboration I was seeking in my science work, but wasn't getting really at scale. But all of a sudden at scale, I was getting it in open source, and I loved it. I really became quite enamored by the social interaction. I've said numerous times that, early on, this was before Facebook, before Instagram, before all these social media or social networks, FTP and email lists, those were our social networks for the nerds back in the day. There was IRC, there was Internet Relay Chat, and these IRC forums existed. And so the IRC and then the mailing lists were the common ways that people would interact. And it was great. I mean, it was just really interesting to go beyond just the people at my university or just the people at where I was studying at the Mayo Clinic, and interact with people outside of my field and get really good conversations going. So so SciPy came about. It was very tightly related to the fact that I was studying engineering and studying biomedical engineering, and it helped. I worked on projects, I worked on modules that I needed, and then a few that I thought I might need. So optimization, and that it just became kind of this list. And then as it's evolved, well, first of all, SciPy quickly became too big. I was way too ambitious, and we were too ambitious, and trying to, I've often said that SciPy was the first distribution of Python masquerading as a library, right? And it was because Python, it was hard to distribute um, if you didn't want to do all the build yourself, which people don't. I mean, one of the things that made the libraries I wrote more popular is when somebody else created a Windows installer for them, right? So, yeah, a high school student, Robert Kern, made the first Windows installers for my multi-pack, like when he was in high school. And what I noticed is there's a lot more users all of a sudden when they could just install exe, as opposed to what I was giving them, which was here's some source code and go figure out how to compile this on your system. Okay, not so easy. So making it easy to install was a big deal.
And what were the biggest challenges, technical challenges you faced while developing NumPy and SciPy?
Yeah. So, well, SciPy, one of the hard things was actually figuring out how to make the integration routines reentrant. So reentrance is um, familiar with integration, double integration, right? So let me see if I can not go too specific, but give enough details so people make sense of this. So Python is a high level language where you end up calling low level code. And an extension module gives that wrapper so that you go from the Python language, you call a function, and then it goes into compiled code, native code, where it executes further. Well, so you're writing this C function that will become compiled code. Well, the biggest thing I had to do was actually call into the C level code because the integration routine was actually in Fortran. And so the Fortran routine, you'd then have to give it a function pointer because if you're integrating another function. Well, that function is then actually called. It was in Python. You were calling another Python function, so you basically be calling an integration routine that would go down into Fortran native code, which would then call out to a function in Fortran that itself would call back to Python, and Python would be called again, right? Okay, now what if that Python function you were calling itself called the integrate routine, right? And then came back again into the code before it actually returned. So that was called this reentrant problem. You'd re-enter the native code, and so if I didn't do anything, you'd actually end up with a problem because it wouldn't. You'd have to set up. You have to set up kind of cache a storage area to copy out to make sure you're not overriding the native code. There's these places where it stores variables, local variables, and so you had to basically set up. Well, you have to set up new local variables to. It's actually the global variables you're trashing because the native code already handles its local variables fine on the stack, but you had some global variables you needed to make sure you weren't just clobbering the next time you called it again. Anyway, so is this formal. That was a hard problem actually trying to figure out how to do that. It was fairly straightforward to fix, but I remember that was a big issue with several codes, ordinary differential equations, integration. Anytime you had a Fortran routine that had to call back into Python to get the function call, right? So that was hard. And then of course distribution, just getting the Windows binaries built was actually tremendously challenging, particularly for complex numbers or functions that had complex numbers they were using. This is stuff I didn't know I'd have to care about, but ended up learning far more about linkers and compilers than I ever thought I would when I was studying MRI and ultrasound.
Have you ever met Python creator Guido van Rossum?
Oh, for sure. Yeah, definitely. Had many very nice conversations with Guido. Um, uh, Guido is very intelligent, very smart guy, very caring about the user experience for people, which is why I use Python. I came to Python because I like the user experience as a scientist. Somebody who I call an occasional programmer. I was more of a programmer than other occasional programmers or subject matter experts, but I didn't want to spend all my time thinking about programming. I wanted to spend my time thinking about physics, thinking about the science, thinking about the problem I had. And Python gave me a place to do that. And it was because of the genius of Guido. But the big time I met him was actually when I started work on NumPy. I realized that a big part of the NumPy problem would be a user adoption. And so there's a social problem. It's not just a technical problem. And so I actually called Paul Dubois, who was the current maintainer, the chief NumPy, the guy running NumPy, and I set up a lunch with him and Guido to talk about the future of NumPy, numeric it was called. If you talk about the future of this ecosystem and how could my ideas and those of others be work together. So we had a very good lunch, very good conversation. I actually asked Guido at the time if we could, and he was suggesting, well, do you want to make numeric part of Python itself? Right? Maybe we just put the numeric object and make it replace the array module in Python. So we talked about that, and I was open to it. I thought it might be a good idea. The reason we didn't was because of the release schedule, and it wasn't numeric. The NumPy effort would take several years. I knew to become perfected or to become to make to steady. Initial release, you want to iterate the releases quickly, and so we knew we'd want to do releases probably every 3 months, maybe every 6 months, and by that time Python was on an 18-month release cycle, so it would have made it difficult at the time. So instead, we talked about getting the structure of NumPy into Python, and that led to the buffer protocol and the memory view object. So those objects are essentially the array structure without all the code, without all the math code.
Right. And what is your perspective on the evolution of Python as the go-to language for data science?
Oh, it's amazing, actually. I mean, I'm thrilled. I think, it was sort of a thing that I thought was what everyone should do, but it surprised me that that it happened so quickly. I mean, not that quickly. It happened. It took 10 years, right? 15 years, one could say. But I'm really, really surprised, really happy with it. On the other hand, it also there's some things that saddens me because I think um, the way it's evolved has lost sight of some of the innovations we created and has actually routed around those innovations to create new problems. So, in some sense, the cooperation hasn't been quite what I'd hoped. Especially around 2012 to 15, all of a sudden, a lot of money came into the equation. A lot of companies, a lot of people, and a lot of those people, very smart people, would start writing things without really talking to anybody else, without really. Whereas we had early on a lot of collaboration, the SciPy conferences, we intentionally had these conferences, had these mailing lists where a lot of collaboration would happen. And I don't think it's a problem of intent as much as it is scale. Like it's hard to get, any kind of human organization is hard once you get past 150, 200 people. Like it just becomes really difficult to get all the ideas. And so you end up with 10,000 people working on problems, and how do you get those ideas percolating and then talked about? But what it led to is that people were essentially reinventing the wheel or doing a lot of work on something they didn't understand very well and not asking, hey, is there a better idea or should we do this? Or hey, just even not really asking permission. I don't mean to imply that because nobody needs to, but just simply voicing or talking about their intentions and then giving a chance for the conversation to arise. Uh, so, in some sense, that's unavoidable. It's always going to happen. So, but I'm one who likes to. I personally like to get as much information as I can to try to make sure I'm implementing the best ideas possible. Which is a hard ask because anybody doing the implementing has to understand the ideas, and that's really hard. Actually, I don't think there's anybody on the planet that understands all the ideas that are actually available. Right? That's the nature of communication and education. Is there is far more out there on the planet right now than anybody understands. Right? And so we're gonna have this. But that's one thing that made it. I loved it, but I also makes it made me sad. It makes me sad to see the lack of innovation, and the lack of sharing of ideas, and the lack of progress because of some of that.
Since we mentioned NumPy and SciPy, I think it's kind of natural now to mention Anaconda. So, what motivated you to found Anaconda, and how did you see its role in shaping the Python ecosystem?
Yeah, Anaconda is a long story. We could talk for at length about it. It's an emerging. It's still evolving as a company. I'm really proud of many things that happened to Anaconda. Um, the foundational reason Anaconda got started is because I wanted to figure out how to help fund open source because I felt and I believed in, and I do believe in the power of markets, the power of companies, the power of entrepreneurship to create trade opportunities. Like I'm a huge believer in and this is it's not it's intellectual belief. It's basically learning about the power of markets and the power of trade and the power of voluntary interactions. And I really wanted to see that work, and I wanted to see it benefit open source communities that I also loved. So, kind of I see the creation of companies as the way to fund and to sponsor and to promote the community engagements that I really valued. So Anaconda was built as a company. We wanted to build a company. And then the specific area, because just wanting to build a company isn't enough, just any company. So, but we saw an opportunity to basically build, scale NumPy, take NumPy and scale it, right? The fact that NumPy worked on a single machine, but people needed array capability that worked on multiple machines. We also saw that at the time, the consulting company we were working out with, Eric Jones again at Nthought, had created Nthought. He was the guy that helped SciPy and helped me create SciPy. I was working with him on his consulting company at Nthought, and they what was working as a consulting practice was to build Windows UIs, Windows applications, Windows GUIs, Windows graphical user interfaces on top of scientific workflows. There were other things that interested, but that was working. But we saw coming down the pipe the web. We saw the fact that UIs were going to be in the web. JavaScript was everywhere. And I didn't, I would often say I didn't want to be writing JavaScript in the future, right? I wanted to figure out, well, can't we make it possible to connect the Python ecosystem to the web too? And so those were kind of the two foundational ideas that we had at Continuum Analytics, which became Anaconda. That's what we started trying to do. And then along the way, we also encountered the main problem people had was just getting stuff installed. And so I previously had experience, but we didn't start trying to build a distribution. We didn't start by trying to build that. We started by trying to do these other things. But just along the way, the thing that had the most resonance, the thing that helped the most people was the fact that we took on this essentially burden. And I remember the time we did it because we were at the Googleplex at the first PyData meetup, first PyData gathering in 2012, and we met with Guido Van Rossum. He was there, and we were talking about the problem of packaging, the problem of it's hard for people to get scikit-learn. It's hard for people to get these packages that are now around NumPy, around SciPy. And he looked at us, and Guido has never been someone who loves the packaging problem. He's not. Every time I've talked to him about it in the past, he's been like, I don't. I just if I want an extension module, I just put it in the standard library.
Yeah.
So he doesn't really
Easy.
have the problem of distribution, or no, he does, but and this is somewhat tongue in cheek, but so it was not his problem. It was not something he thought a lot about, and so it was always left to other people, and other people. It's a hard problem, and so he told us that, well, you're probably gonna have to solve that yourself. So if you need that, then you're gonna have to solve it yourself. And so we said, okay, I guess we will have to do that. And so we wrote Conda, right? And the purpose of Conda was just to get stuff installed, and then coming full circle, once we wrote Conda and realized how easy it was to basically recreate environments, throw them away, recreate them again, and install whole package sets together that work together, it changed everything for me. It changed a lot because I realized how much of SciPy was really a distribution problem, and it was trying to get all this stuff together and installed in a single exe. Right? A lot of the sci-fi work was that, because it really is hard to have a big overarching project that encompasses so much capability. Like, you look at all the pieces in Anaconda, and there's no way that a single group of maintainers can be in charge of that much capability. Like, you have to build a tree structure. You have to build it so that smaller groups of people can be responsible for the delivery of a thing, but then somewhere that's pulled together to make the install easier. Because this is the dichotomy. We've seen it multiple times. You'd have a commercial package which was, oh, here install MATLAB, or here install IDL, or install Mathematica, and it's so easy because it's all coherent. There's a product story, right? There's a coherent product mind and kind of a single person. Whereas open source is kind of the opposite. It's about this groups of thousands and hundreds of thousands and millions of people that are contributing to their pieces, to their subunits, subprojects. And so open source tends to want to have things distributed and spread out and smaller groups, but then the integration problem is bigger. So, so how do you pull it all together? So Anaconda only emerged is really after the first 2 or 3 years of founding Continuum Analytics that we saw how important this problem was. And we just tried to solve it with a package and environment manager. Conda released it and got a lot of adoption. It just it surprised me how much um, I didn't expect even that much. And so that's where Anaconda came from. Basically, we were trying to solve some fundamental problems, and we did do some things. We created Bokeh. We created there's several libraries. There's Panel now, and then we created Dask, and we created Numba to help scale Python up and out. These are really important things that we built as open source projects. But then the product that really helped us grow as a company was uh, these binaries, these secure, tested, trusted, optimized binaries that people could get. So that's how kind of Anaconda evolved. But it came from my desire to create a company so I could support open source. That's why at the same time we created Anaconda, I also created with some other people NumFocus. So NumFocus was created as a nonprofit that would own the IP to the open source projects we cared about, the community open source projects, because I didn't want the perception to be that Anaconda owned NumPy, or the Anaconda owned SciPy, or the Anaconda owned whatever else might emerge. And so for me, the natural progression is you start with a group of people that build an open source project. But as it grows and becomes community driven, there's like 100 or 1,000 people involved. It's not like a single company should really own that, even though they might start owning it. So even with Anaconda, we Anaconda owned Dask, Anaconda owned Bokeh. Eventually, those now are owned by NumFocus as the community driven. The IP of those is owned. Now, Anaconda still contributes and promotes and supports, but so we created this NumFocus to be an IP holder. It's a very important part of the strategy, and not just the strategy, but the like that makes it sound like it was the mission, the very important part of the goal of what we're trying to accomplish, which is enable open source to thrive.
Okay, and how did your vision for Quansight come about, and what challenges did you want to tackle with that company?
Yeah, great question. So Anaconda grew to the point where it could use additional leadership, more product-led leadership, and so Anaconda hired new CEO leadership. And at that point, it became, I was eager to ensure that the other aspects of what Anaconda was doing were continued, and so I worked out with the leadership, the investors and the board and the new CEO to leave Anaconda and start another consulting company. So the idea with Quansight was to start essentially recreate the foundations of what was Anaconda. So Anaconda got started with these two ideas in mind, and then we ended up creating a consulting company with open source innovation, and then a product emerged from it. And so the idea of Quansight was to recreate the foundations of that, but structure it so that more than one product company could emerge. So it wasn't just Quansight would have all the products, but it would be a consulting company. Then we intentionally created Quansight Labs, which would be a not-for-profit open source research lab. So work on and particularly finally fulfill my goal of starting a company in the first place, which is to have people working on NumPy and SciPy. And then Pandas and Dask and a variety of other open source projects, depending on the people that join. I'm actually, one of the things I'm most proud of with Quansight is that we did create Quansight Labs, and Quansight Labs has been able to hire people to work on NumPy. NumPy 2.0 was and really cool features in NumPy, like the new data type, the new string data type, the new capabilities in NumPy have been funded by people written by people working at Quansight Labs, which Quansight Labs was able to fund. So that was a big important part, was create a research lab that could work on open source and be sustainable, be funded. So it's not a for profit, but it has to survive. So it has to make as much money as it spends. And then Quansight Consulting does consulting work with companies that are trying to use open source effectively. So that was the idea, to recreate that. Then we added a third component, which was an investment arm and an incubator arm, basically an arm that could incubate product ideas so that if they came out, we could spin out other companies, product companies that might emerge from the innovation that occurred at Quansight.
Mhm. And what is your vision for the future of data science and scientific computation?
Oh, it's a great question. I'm open to conversation there. I mean, I think Python will continue to be an important part in the conversation. There'll be a lot of new Python users for many years. There's a lot of, AI, of course, is everywhere, and people are excited by the future of AI. I am too, but I'm excited by what languages will AI be writing? What code will AI be generating? I think it will be generating Python. I think it'll be generating other typed languages. So I'm excited I'm particularly excited right now for what I'm calling typed Python, a kind of a typed Python standard. I'd really love to see more standardization around the existing typed Pythons that are out there. They exist. Things like Cython exist. Cython is a kind of typed Python. MyPy is a typed Python. Numba is a typed Python. Jax. Jax is a compiled version of Python that's a typed Python. Essentially, it's a subset of Python where the types can be used for optimization.
Do you believe there are any programming languages that might challenge Python in Python's dominance in data science world nowadays?
English.
Okay, English. That's
Just
interesting.
just just English, English language. And I say that because Python achieved its heavy usage because it was able to be a language that domain experts, data scientists would use and reach to that didn't require them to learn pointers and abstract syntax and class structure and a lot of programming concepts. They could just kind of write function calls and write code. In a world where AI can generate code for you, all of a sudden, will some of those people just write English and then it will generate the code they want. So that's why I say it. I say it because in the future, I think it'll bring a lot more people to the story who are essentially using English to create code. I think that code will still be Python, but perhaps they kind of formalize or a more structured Python, perhaps.
And do you believe that the developers should be afraid of AI, that AI will take their jobs soon in the future?
No, I don't think they should be afraid of it. I think they should be aware of it and savvy to it because I think what will happen is AI will take over um, mundane developer jobs. So, in some sense, if you're counting on kind of the mundane developer job to you don't have to learn more. You're counting on, oh, I have this secret knowledge and I'll just be able to use it to do work forever. Maybe that isn't true, but I think there's the old adage that I believe that your job won't be replaced by AI, but you will be replaced by somebody who uses AI to do your job. So I see it as a tool. I see it. It's not going to replace you, but it's going to be a tool that you can use. And if you get good at it, you'll continue to have lots of work. If you ignore it and pretend it doesn't exist, then maybe. But that process will take 5 to 10 years. It's not going to be happening overnight.
I see. And what do you think of the role of machine learning and AI in general in the future of scientific research? Will AI be capable of writing scientific papers, maybe?
Um, good question. I think AI will be capable of inspiring people into what they should study. So it'd be help. I mean, it's a good creative kind of a creative brainstorming tool. And I think it would be helpful for people. Current incarnation of language models. I mean, AI is a big topic. Like AI, newer AI models, I think potentially could and will help us with scientific research. I think we are a long way from having a computer replace the human mind. Um, Maybe that'll happen in my kid's lifetime, but I'm excited by just the fact that we have more capable tools that we can use to learn more. The digital twin capability, right? The fact that we can actually create in digital form systems that mimic parts of the human mind is interesting, right? It's clear we've been able to build a very nice language model, which is causing us to think about, well, maybe part of our brain is just a language model. How does our own consciousness work? So I'm excited by just that process to learn how we work because of AI and how it can help. Because the process of scientific discovery is a very human process, and it's a process of I think it can help us formalize. This is already happening where it can help us just with design of experiments, with what kind of tests to run. It can automate a bunch of tests. A lot of things that would be painstaking and hard to do, take many years. We can do it quickly with AI. I think there's a lot of that. Um, but we'll still need. I think we're one of the questions I have is what will happen when AI takes over some of the mundane jobs that we use to actually train the future of scientists in the future. Like this, we're already seeing this is how do we transmit knowledge and practice of science to the next generation? That will be affected, and it won't stop the process, but it can alter it in potentially productive ways, but also potentially ways that um, create some loss of knowledge.
What do you think of quantum computation? Do you think that quantum may be like overtake classical processors in the future?
No, I don't think so. I'm actually pretty quantum negative. I don't mean to. I like quantum devices. To me, quantum devices are a kind of analog computer, right? And I like analog computers. I like optical computers. And so I think they're interesting, and I certainly believe they'll have a place and a role. I just don't think they're going to be as universal because they're going to be finicky. They're going to be hard to program. They're going to be able to be used for very specific applications. Um, and so I think they're interesting, but I don't think they deserve the hype that they sometimes get. I think it's an example of people are always looking for things that can get funding, right? And the idea of and quantum, you kind of tying into a cultural trend because quantum is still not well understood by a lot of people. You can kind of and they can imagine there's this cutting edge new boundary of computing that could call it quantum computing, and that'll unleash all this capability, just like we had the revolution that computers have brought. I think we do a lot of borrowing from that, essentially science fiction thinking as its core, I don't think it's gonna be that huge. I think it's gonna be helpful, but not that huge.
I see. What projects are you currently most excited about, either within or outside of your Quansight?
Yeah, so I'm very excited about, company growth, actually. I really wanna help people create companies and find incentive structures to align, uh, productively the human population. I love it when I see great feedback loops between and that cause people to become countries and societies to become wealthy, to get out of poverty, to eliminate some of these the the Malthusian negative dramas that occur in human societies. It's just how do we have more prosperity? So I love that, and I love participating in that. On the technical side, I'm really passionate about packaging still. I think I'd like to see, in fact, I'm a real proponent of environments over package managers. I think there's been a lot of enthusiasm over package managers, but the actual use case people care about, the end user really just wants their stuff reproducible. They want their stuff to work and to share it with others. And whenever you're sharing things, you're not sharing a single package, you're sharing a package set. You're sharing a whole collection of things that have to work together well, and you want that to be reproducible. And so I'm excited by that kind of, lock files and spec files and kind of I'd like to see more evolution in that world. And we've got some ideas we're working on to try to improve that. So that's a whole area I like. Then the other place is this, I referred to it before, compiled Python, typed Python, um, bringing together. Like I would love to see a hybrid between Python, NumPy, MyPy, and kind of in a way that is actually a language people can specify AI models in, they can specify code in, and then it compiles to code that can run. It doesn't require it's fast, it's efficient. There's a big opportunity there to actually essentially create a new kind of language that's very related to the Python that exists out there now. So, I call that typed Python. There's some examples of it. There's a static Python project by a friend of mine that I know. There's several versions of this, so it's probably more of a standardization and more of a specification, and then a reference implementation. So I'm excited by that. I'm trying to figure out how to fund slash find people to work on it. That's what I'm excited about.
Right. And what advice would you give to aspiring young developers who are looking to make contributions to scientific computation?
Yeah, great question. I would say there's plenty to do. Find something you care about and work hard at it. It's not like the hole you're digging. You can't just dig a few. You can't just dig a little bit shallowly in the dirt and throw it and hope something will happen. It actually does require quite a little building, and anything meaningful requires significant building. So, um, if you're just looking, you have to be serious, and so you have to care about the thing. So, find something you like, find something you care about, find something you're passionate about. You want to spend, at least 3 months working on, right? You'd have to be willing to spend at least like 12 weeks of your life every day for, 8 to 12 hours a day working on that thing. And if you don't feel like you wanna do that, then don't then you won't spend enough time. And that 3 months probably will turn into 3 years if it works, right? Because maybe it doesn't work and you give up after 3 months, right? Okay. But if it does work, you're going to spend a lot more than that 3 months. So you have to care, and it doesn't happen overnight. A lot of times, I think one of the deceiving things about the world is you see people that accomplish something, and you think, oh, because it kind of rapidly, as far as you're concerned, it happened rapidly, but it didn't. Like Python was written, first released by Guido in 1991, right? 1991, right? I didn't even start using it until 1997, right? And then the work I did with NumPy, like the first release of a library was in 1998. SciPy wasn't released till 2001. Didn't get really adopted till 2004, right? Every open source project I've done that's been successful has taken 18 months to 3 years to really catch on, right? So have patience. You can't have patience if you don't care about it. You have to care, and you have to believe in it and believe what you're doing. So that's the advice I would give is find something you believe in and learn and keep learning and be open to learning. There's more. I still feel like there's so much I don't know. I have to learn, and that's the fun part. Is that's always going to be you'll have a life of joy if you enjoy learning and you continually seek to learn. You'll have a life of joy. So.
And what were some of the most surprising cases, use cases for NumPy or SciPy that you have seen over the years?
Oh, um, that's a good question. I was a little, I wasn't, I was a little surprised by the use in the finance world, actually, um, just because I thought that was covered pretty well by other tools, and I was surprised by how much the financial world used NumPy and SciPy, because I wasn't aware of the derivative markets. I wasn't aware of just how much scientific computing goes on essentially in those markets. So it should have been surprising, but it was surprising. Um, and then I kind of um, yeah, that's probably the most surprising. A lot of other uses are I've been more surprised by how people use it than the fact that it's used in that space. It was really surprising, for example, to see a C++ library essentially get functionality to that library by calling a SciPy function. So they're embedding Python in a C++ library to get functionality to a C++ programmer. That was surprising. Right, so I didn't expect that, but that is that happened.
Right. And what are some of the most common misconceptions about open source software in general?
Oh, I think one misconception is that open source software is always the best answer, right? It constraint surface that leads to open source does not always mean you get the most technically correct solution, right? That there are actually some great solutions out there that are better than a popular open source library. So sometimes people think that, oh, open source has all these people with it, and so then from that emerges the best answer. That's not quite true. That's not always that's in fact rarely true, honestly. I think it's just a satisficing. It solves the constraints, and it's good enough. And then these other constraints of usability and investigatability, the fact that it doesn't anchor you, you can swap it out for other things. I think that's one misconception. I think the other misconception is um, that it's hard to apply it commercially, like that you can't make money with open source, right? Some people think that, but there are actually very clear ways to use open source as it relates to business and how to make money from it, quote unquote. I would say align incentives and create prosperity in your life by participating in open source ecosystems.
How do you see the role of education evolving in the data science field?
Um, Becoming very much more personal. I really like the flipped classroom idea that I've heard people like Lorna Barba talk about, and then I see as much more appropriate. The flipped classroom is the idea that you actually learn outside of the classroom and you come together to ask questions and to get help, right? It's not you're just getting lectured to, right? That I think AI will just accelerate that because effectively with an AI tutor, you have your own personal story. And so a lot of times I think coming together will be more you getting a chance to teach other people. So I see, you learn so much more when you have to teach somebody actually. And so kind of micro teaching to other subgroups as this kind of feedback loop of you teaching people about one thing, everybody learning things, and then teaching each other about other things. I think that kind of thing, and then basically somebody facilitating that engagement is a model for an education that it doesn't require the kind of hierarchical modes that we have today.
Do you think that Python's performance limitations will need to be addressed in the future, and how?
Yeah, I mean, depends on what you mean. I mean, yes, performance limitations will always need to be addressed somewhere because if people can take advantage of a thing to be faster, they'll use that thing. In the past, it's always been the extensibility of Python. Python's extensible enough that you have the fast thing, cool, just link to it and call it. And Python's a high level script. I don't think that'll change. One of the reasons for typed Python is I want people to be able to write the fast code in still a Pythonic-like language. I don't want them to have to learn some other whole new syntax to be able to write fast code. So I'd love to see Python used more for that too. But to do that, you actually need a runtime system, kind of again a hybrid Python, Numba, JAX, Tensor, Torch compiled like system. Like right now, they're literally, LPython is one. If you go to the lpython.org site, you'll see the 20 to 30 typed Python dialects that are already out there. So I see the need for definitely the need for optimized Python, optimized runtimes. Future.
So, if you were to start your journey today, what would you do anything differently than when you started?
Sure. I mean, not fundamentally different. I still would probably start with something I care about education wise. I'd learn what I loved about my education is I learned a lot of math, and I would still learn a lot of math. So I learned a lot of math. Then I would start applying that math with computation. I would probably do differently as I would collaborate more quickly. Even I would get involved with others more quickly and learn from them more quickly. Um, Not be afraid of getting your stuff corrected. Like I think early on, especially, I was very hesitant to share what I had because I didn't want to be seen as dumb or I did something wrong, right? And I would basically just recognize actual people criticizing my work is actually engagement and a good sign. Like the opposite is it's actually just getting no response. That's harder, just engaging with people and trying to get any response more quickly. So I'd probably more. I mean, I was collaborative, but probably even more so. Just try to really get and meet people in person. Not all the time. You can do a lot online, but not be afraid of gathering. 4 or 5 times a year, at least twice a year, but just being in person.
Yes, and the final question. What's the legacy you hope to leave behind in the world of scientific computation and open source software?
I would love to leave a lot of people who are enabled. The biggest compliment I get is when people tell me how much it helped them in their career, in their schooling. I love that, and so I would love to see. I love that. I love people being able to be empowered and enabled. I would love to see a lot of people who be able to create companies and who are able to create innovation. And then I think where I need to do better. There's a lot of stuff in my head that I haven't written about. I haven't talked about. I haven't published. Not in the sense of formally publishing papers, just share some of the concepts that I think might help people. So I'd love to be help people to build technology, build companies, and build relationships with each other. Um, that's probably the biggest thing. And open source projects. I love seeing the open source projects that have flourished, and there's new ones all the time. Helping people recognize to be patient with those projects, like just a little bit of the information about don't uh, th- things that are worth it take time and they don't happen overnight because you're dealing with people and people require a certain change timeline. People don't just instantly change who they are, just like you don't, I don't, and everybody else is the same. And so any adoption curve takes time. Um, so yeah, just just be a source of help for that. I guess that's the biggest thing. I just love I love the fact that people have been helped by the stuff that I did. I had a desire to help people, but I was just trying to solve a problem I had. I think that's the most important thing. What I see a lot of people do today is try to predict. And it's fine to predict, it's fine to think, but it's almost like they're following a trade rag or they're following a news magazine and they're saying, "Oh, this is where people are going to care about, so let me go kind of work in this space with something." Like I would encourage people to actually look at the problems they have, look at the things they're trying to solve, and start there and maybe iterate a little bit. Solve the problem you have and maybe add a little bit more you can imagine, but you really fall into danger the more you try to build outside of your area of real awareness and that experience. The more you try to build outside of that, you really got to have a tight feedback loop because most of the time you just build stuff nobody really wants. That's been true for me. That's been true for a lot of people. So build the stuff. I think the big part of open source is people built stuff that they wanted. And it turned out other people did too because they had similar experiences.
Wonderful. So, Travis, thank you so much for this conversation. I really enjoyed it, and I would also like to thank you for your time.
Thank you. I appreciate Hrvoje.
Yes, Hrvoje.
Yeah, Hrvoje.
thank,
Thank you so much.
thank you so
Apologies
much.
for the name, but I really appreciated talking with you. You've been a great
Thank you
host.
very much.